Good morning, everybody. I'm Sonu Mehta, and I'm going to talk about a tool called Rex that uses correlated change analysis to prevent misconfigurations. This is joint work with a bunch of other people from Microsoft Research India. So let me start by describing a scenario. Alice is a new developer who has recently joined a team, and she's given a task to rename old microservice to new microservice. She goes ahead, makes changes in file registry entry.xml. Along with this file, she is expected to make changes in 3 other files, which is ITAR load balancer, common load balancer, and firewall rules.xml. But as these things are not documented very well, she goes ahead, makes changes in 2 of the related files, but forgets making change in firewall rules.xml. Again, as these things are not caught by the compiler, the code gets checked in, and boom, it leads to service disruption. So in this case, as you saw, a small missing configuration change led to a huge service disruption. And this was not a contrived example. We took this example from one of the Office 365 repositories within Microsoft. This problem is not really specific to one company. Various companies like Facebook, Amazon, Google have faced outages because of these misconfigurations. As these large-scale services become more complex and more configurable, failures due to misconfigurations have become a serious concern. And all this motivated us to delve deeper into this space. The very first question that came into our mind is, why do we need configuration files at all? Well, based on our case study with different large-scale services within Microsoft, we realized that these services are very dynamic and agile. They have hundreds and thousands of knobs present in them to determine their behavior, and these knobs are used for various things like gating feature rollouts, running A/B testing experiments, updating machine learning models, etc. Every day, hundreds and thousands of such changes are made to these config files, and all these changes have to be made without application redeployment or restart. So what I mean here is, if all these configuration parameters are actually made part of the code, and if we have to make 100 changes every day, then the code or service needs to be redeployed 100 times a day, which hampers the dynamism and agility of these services. So this kind of justifies the presence of configuration files. But then the second question is, why is configuration management so difficult? Again, based on our analysis, we realized that across different large-scale services, there are varieties of configuration files present, and the correlations or dependencies across these configuration files emerge organically, and is very different from one service to another service. Unlike code, which has great syntactic and semantic structure, configuration files lack that rich information, and so no compilers exist for configuration files. Moreover, it's very hard to document all these correlations manually because they keep changing frequently. So just take a look at this plot. This shows the increase in number of XML files in just one repository within Microsoft. In last 12 months, the number has increased. It's simply doubled from 3,500 to more than 8,000. So imagine how big the number would be if we include all types of correlations and all types of configuration files. So in general, configuration management is a big space, and we are not the first one to deal with this problem. People have tried to work on this problem in different ways. So this paper at Facebook talks about holistic configuration management, where they have used code as a config as a code approach to generate configuration files. But as part of this, the invariants for configuration files need to be manually defined by the developers, and that becomes a problem when they have to scale it to hundreds and thousands of configuration files. The second paper at SPLOS 2014 talks about a technique called Encore, which is used for misconfiguration detection. Here they use state-of-the-art association rule mining algorithms to detect correlations across files. But again, they have to, since the state-of-the-art association rule mining algorithms are not able to scale well with the increasing number of configuration parameters, the developers have to manually define certain templates to guide the learning process, and this becomes a challenge when new files are included in the system. So all these techniques try to solve configuration management in some or the other way, but the manual input becomes a challenge when they have to scale to thousands of configuration files. So we decided to come up with a more generalized approach, and we have developed a tool called Rex that uses correlated change analysis, and it's a completely automated tool. With the ubiquitous use of version control systems like Git, we have enough information available about the historical changes that have been made to configuration parameters in the past. So instead of asking developers for manual input, we exploit that information to learn these correlations. So now I'll be explaining the technique of Rex in detail. Rex, as I mentioned, is a correlated change analysis tool, and it's a two-step process. The first step is change rule discovery, followed by change rule refinement. So let me start by describing the change rule discovery part first. Change rule discovery is nothing but a market basket analysis on top of commits data. A commit is a set of changes, code changes made by developer at one point of time. A group of such commits is input to an association rule mining algorithm, which in our case is FP growth, and this algorithm outputs a certain set of correlations or rules. This idea is inspired from Tom Zimmerman's work on mining version histories to guide software changes. So as I mentioned, the algorithm outputs a certain set of rules, which are essentially the correlations across files, and this is how a typical rule looks like. What this means here is, whenever a change is made in file X, which in this example is content filter spamrule.xml, we expect a change to be made in file Y, which is post-content filter spamrule.xml. Each rule has two additional parameters called support and confidence. So support is essentially the frequency or the number of commits in the past where both files X and Y would change together. And a confidence value of 0.8 here means that out of 100 commits where file X was changed, in 80 commits, file Y was changed along with X. So we can actually consider Rex as a rule learning engine that learns these correlated config changes, and then this rule learning engine can be used for various things like coming with a domain-specific compiler or as a suggestion engine. Now, as part of suggestion engine, we can make recommendations to developers when they have changed some of the files and they forget changing some of the correlated files. These suggestions can be made in a development environment when the developers are actually making changes in a code editor, or it can be made at the pull request level when the developers have committed the changes. Currently, Rex is deployed as suggestion engine that makes recommendations at pull request level, and it is enabled as part of a bigger project within Microsoft Research called Sankey. So this is how a typical suggestion would look like to a developer. In this case, a developer is recommended to edit file sandbox.pfxmappings.xml because they have edited some of the correlated files. In addition to this, we also provide information about the previous PRs where these two files happen to change together for interpretability reasons so that developers can understand how these files are correlated. So we got the system deployed on about 50 repositories for a couple of months, and we realized that even though Rex was able to catch high impact misconfigurations, but at the same time it was generating a lot of false positive recommendations that the developers did not find useful. And the reason was because this change rule discovery is a coarse-grained approach and it doesn't really take into account the actual diff content. So what I mean here is we're doing all this analysis at the level of files, and so even if a developer goes ahead and adds a new line in the file or adds a comment in the file, we would still end up making a recommendation for file Y, which we would not like to. So this motivated us to work on the second part of Rex, which is change rule refinement. As part of change rule refinement, we wanted to understand what kind of change in X triggers a change in file Y. So let me take an example. Here, for file X, we saw that whenever a version was updated for a particular reference in file X, the same version for the API was updated in file Y. But when a reference was added for file X, there was no change in file Y. So essentially, this file pair was related on version updates and not on the addition of references. And this relationship was very different for every file pair. So we wanted to learn for every file pair what kind of change in X triggers a change in file Y. As part of this, we have built this pipeline where the input to the system is a set of changes for file X. Then we categorize them into different clusters based on certain attributes. And finally, we use an age-old inductive generalization technique to learn the most specific generalization of changes in file X that triggered a change in file Y. I'll be talking about all these things in detail. Let me start by describing what I mean by most specific generalization. So again, let me take an example. Let's say for file X, there were 3 commits in the past, and in all the 3 commits, there was a change made in command config node and network. So X is an XML file, and all the 3 commits, there was a change made in the command config node. Now, if I look at these 3 commits, one generalization of this change could look like this, where I simply say that something was changed in file X, and I do not know what. So this is nothing but change rule discovery, the phase 1 of Rex. Another generalization of this set of changes could look like this, where I say that something was changed in network node, but what exactly is changed, I do not know. What I am interested to learn is this kind of generalization, where it is clearly specified that the change was made in command config node within network node. This is the more specific generalization, and we use a technique called anti-unification to learn this more specific generalization of the set of changes. The reason we opted for anti-unification is because we realized that the configuration files have some sort of structure present in it, and this technique helps us to exploit this structure very well. To use this algorithm, the first step is to generate the diff data. So again, taking back the previous example, in this case, there was a change made in command config node, and if I just extract the text diff out of it, this is how it is going to look like. So for first example, the text diff is enable IPv6. Similarly, for other two examples, these are how the text diffs would look like. Now, if I just concentrate on the right end of the slide and just do a generalization on text diffs, I end up learning nothing because there's nothing common in the text diffs. But if I expand the context around the change, around the text diffs where the change was made, and include the nodes, which is command config and network in this case, I can learn something meaningful, and I can learn a generalization that is shown as the highlighted box below on the left hand side. So for all our analysis, we include context expanded diffs. So once we have the context expanded diffs, the second step is we convert these diffs into trees. So again, taking back the previous example, this is how the tree would look like for first commit. Here the root node is network. It has two child nodes of type attribute and third child node of type command config. I've highlighted the difference in attribute values with green and command config values with blue. Similarly, the trees for other commits can be created like this. Once I have created those trees for context expanded diffs, then I run a set of two rules to extract the common subtree out of it, which looks like this. And the differences in the trees are replaced with asterisks or holes. Converting the tree back to XML node, we learn the most specific generalization for the input set of context expanded diffs. So this explains the inductive generalization part. Now I'll explain why do we need to do clustering before we do this generalization. So again, taking back the previous case where change was made in file X, we saw that all the changes were made in network node. What if we consider another scenario where in addition to these three commits, there were two more commits, but in this case, the change was made in third group node and not the network node. So before doing generalization, we cluster them into two categories based on network node, based on the node type and attributes. What if we don't do clustering? If we don't do clustering and randomly pick two nodes from two different clusters and start doing anti-unification, we would end up learning nothing because there's nothing common between nodes from different clusters. But if we do clustering in the beginning and then start doing anti-unification, then somewhere in the hierarchy, we learn more specific generalizations for individual cluster. So the highlighted boxes are the most specific generalizations for individual clusters. So once we have learned these more specific generalizations for individual clusters, what we do is we enhance the rules that we learned from the first step of Rex, which was change rule discovery, with these set of generalizations called G. So this concludes my discussion on the change rule refinement part, and now we have an enhanced set of rules. Now, instead of making a recommendation for file Y every time when X was changed, we make a recommendation for file Y only if the change made in X matches one of these generalizations. So as I mentioned, Rex is a tool that has been deployed widely at scale within Microsoft. We started working on it about 2 years back. We got the first phase of Rex, which was change rule discovery, deployed in about 50 repositories in June 2018, and we got the final version of Rex deployed in July 2019. Currently, it is deployed on about 360 repositories. It processes more than 1,000K pull request updates per day. And till date, it has made 5,000 such recommendations that developers found relevant, and they acted upon it and actually made changes in those files, which helped them prevent those misconfigurations or service disruptions. So let's talk about evaluation matrix for a recommendation system like Rex. So for a given test set, let's say Rex detects 100 correlations. Out of these 100 correlations, 80 are true positives and 20 are false positives. So in this case, the model precision would look like 80 by 100, which is 80%. This is a pretty high number, but the challenge comes when we want to deploy it to the developers. In general, developers are smart and they're not going to forget all of these correlations that Rex has detected. So out of these 80 true positives, they would still remember 72 true positives, and they would still make change in them. They would at max forget maybe 8 true positives. But as a recommendation system, we would be suggesting developers for these missing files only if they have not made a change. So in this case, we would make recommendations only in the 8 missed true positive cases and 20 missed false positive cases. So essentially, in this case, there were 28 recommendations, out of which 8 are true positives, and our deployment precision looks like this. So as you can see, the deployment precision comes out to be much lower than model precision. But each true positive that Rex figured out actually helps developers save millions of dollars and hours worth of time. So we have selected 6 repositories from various services like Exchange, Azure, OneDrive, and Dynamics CRM for evaluation purposes. So the second and third column talks about model precision with and without change rule refinement, and the last 2 columns talk about deployment precision with and without change rule refinement. And as you can see, the change rule refinement helps increase in precision both in cases of model and deployment precision. On an average, we're getting about 20% deployment precision across all the repositories. So this was quantitative analysis or quantitative evaluation. We also did qualitative evaluation by conducting an extensive user study. We sent emails to about 328 engineers working across 5 different teams, and the study was conducted in 3 phases. As part of this, we realized that in addition to this hard true positives and false positive numbers, there is also another category of suggestions that developers find relevant, but they do not act upon it because of various reasons. Either they are busy, or they have some other high priority work, or they make changes in a separate pull request, which a system is not able to capture as a true positive. We found that 63.4% of the users found the suggestions relevant, even though our deployment precision was around 20%. And about 43.8% of the true positives that Rex recommended were high impact, and they actually helped save service disruptions or failures. So these are some of the anecdotes from developers. So in general, configuration management is a big space. With Rex, we have just added a drop in the ocean. We have taken a small problem really deep and built an end-to-end system, got it deployed, and currently hundreds and thousands of developers are using this. As part of developing this tool, we have gathered a lot of domain knowledge, and we want to take this further by generalizing Rex. Our idea for future work is to use techniques from program synthesis, machine learning, to come up with a holistic approach towards configuration management. So to summarize, failures due to misconfigurations have become a critical problem. For this, we have built an automated tool called Rex. Currently, it has been deployed at scale, and we have made about 5,000 recommendations that the developers have found useful. Thank you.
Questions? This one, Aaron.
Aaron Gumber-Jacobson, Colgate University. I'm curious if you've thought about how templates might play a role at all, where maybe the same thing is copied in multiple configurations with some changes to some of the fields of it, and whether you look for those types of things or whether that's sort of automatically captured by this generalization.
Yeah, so good question. So some of the related work talks about templates, but the thing is we have variety of such correlations, and templates won't be able to capture all of them, because as new files get added, we have to define new templates for them. So this generalization takes care of that, and it automatically learns those templates.
Okay, Ben?
So I know that you've talked about this specifically for configurations. Have you tried applying it to other things, such as general purpose software development?
Right, so we applied it for code files also, and we realized that it didn't turn out to be very useful because a lot of these things are already caught by the compiler. So we are making recommendations at pull request level when the developers have already built the code. So these things are caught by the compiler, and we essentially do not catch up a lot of mistakes there. Yeah.
Thank you, Sonu.